Okay, so now I've got a cool model going on here. Back to my bromine model. All right, and what I want to point out is this is very, very similar to the Lindemann-Hinshelwood mechanism. Okay, so here on this mechanism, I'm looking at now a bromine undergoing thermal decomposition into a Br radical plus a Br radical. Okay, so we could do that. Actually, let's get really fancy with this thing, right? And I'll draw the Lewis structures. Okay. So bromine and for the most part, the halogens are somewhat stable as radicals, okay, because of their valence shell. So now I get one bromine radical and another bromine radical, okay? So, but how the hell does a bromine just do that, right? How does a bromine just fall apart on its own? Well, it doesn't, okay? It needs one of these collisional partners to slam it and cause it to break, to cause the bond to break, okay? So there's very much a Lindemann-Hinshelwood mechanism going on here with the thermal decomposition of bromine. The only difference being in this, in the full Lindemann-Hinshelwood mechanism, now these unstable products here go on to form a stable product. I don't have that going on here, okay? Instead, rather, these two bromine radicals can now recombine back to our original bromine, okay? And of course, what I'm not showing you here is that second body. In the case of the equilibrium reaction, and this reaction, it would be a third body, right? But now this gets really interesting. And so what I've done in my Mathematica model here is two different things, all right? So I talked about how oftentimes, or sometimes rather, this M could be another A, or it could be an unreactive partner like a helium or an argon, all right? So I first solved this model in the case in which, here we go, where M equals another bromine. So right here, M equals Br2. So this would be like two Br2s colliding with each other. One of them falls apart into an unstable set of radicals. The other Br2 is still available to react, okay? What I've also done in this model is I built up a manipulate for temperature, and I built up a manipulate for the concentration of bromine, which is basically another way of saying the pressure, all right? So what I've got going on here now, this is a power function of Br2. So at 0, that means I've got 1.0 molecules per cubic centimeter. 1 molecule per cubic centimeter. I mean, that's less than the pressure of outer space, okay? And at 300 Kelvin over 10,000 microseconds, which is 0.01 second, nothing's gonna happen. And as you might even guess, even if I crank this thing to 1800 Kelvin, nothing happens because I've only got one bromine molecule per cubic centimeter. So I am definitely under the low pressure limit of this reaction, and I'm way, way below the low pressure limit of this reaction. At 1 molecule per cubic centimeter, nothing reacts, at least not over the 10,000 microseconds, okay? But now check it out. When I go up power of 1, I have 10 molecule per cubic centimeter, now 100, now 1,000, now 10,000, and so on. And you can see even at 1800 Kelvin, to get these bromines to start reacting, you know, over a fairly quick period of time, 0.01 seconds, I've got to crank this up. Now, here we go. I finally started seeing some action. There we go. At 10 to the 15 molecules per cubic centimeter. So that's the equivalent of 1 times 10 to the minus 4 atmospheres. So that's still a pretty big vacuum of bromine, because remember, in this model, there's nothing else around. I don't have any gas bath. So this is still 1800 Kelvin and about 10 minus 4 atmospheres. Here's about 10 minus 3 atmospheres. Here's 10 minus 2 atmospheres. And then here is 0.1 atmospheres. And then there's 1 full atmosphere. And what you can see is we've achieved equilibrium. And we've achieved equilibrium in this reaction quite fast, right? So there's some equilibrium amount of bromine and Br2. And this is really interesting, this case in which this M is another bromine, because what's happening now is my bromine radicals are constantly recycled back to more Br2, okay? There's no loss. They're just cycled round and round and round. So it's a true equilibrium as indicated by these profiles. And now, as you can see, when I turn the temperature down for the same pressure, we're actually going to see a Le Chartier's principle going on here, right? We're actually going to see the rate constant reduce as a result of turning the temperature down, which there you go, right? You can see it. The rate constant's getting smaller and smaller because the ratio of bromine to Br2 is getting smaller and smaller. So this is really cool. And in fact, you can see that even at 1200 Kelvin or so, I can obviously find some point where the reaction is slowing down, where I'm not going to see it over this 0.01 seconds. But now if I just keep it, let's say I'll keep it at this 1300 Kelvin mark, and I'll play around with turning the pressure down again, okay? And so that has now the same effect as turning down the temperature, but I'm turning down the number of collisional partners. So that really influences this reaction, okay? So let's leave it at 1019 molecules, so roughly 1 atmosphere and 1300 Kelvin. And now I'm going to show you something that's entirely different. So this is now bromine decomposition with an inert bath gas at 1 atmosphere. So what I've got going on here now, same reaction, except for I've called M something like helium or argon, something that's not going to react. It can still act as a collisional body, okay? It still helps take away or contribute to the momentum of the reaction, which I'm going to get into a little bit more detail in the next lecture, okay? But now the only difference being, with M being an inert third body, there's no recycling reaction to take me back to Br2, and I'll prove that to you. So I'm going to go up to about our 1200 Kelvin or so. Really fundamentally interesting with this going on and only 1 molecule per cubic centimeter, because there's no recycling agent, it reacts. But now, as I turn up the bromine pressure, something interesting is going to happen. I hope it's not making a liar out of me. Oh, there we go. Yes. Okay. So let's compare these profiles. Okay. So here is, I did that at 1300 Kelvin. Let's turn this up to 1300 Kelvin. Okay. So same condition. This bromine reaction in which the second body is another bromine. So this gives me a true equilibrium, formation of bromine radicals back to stable Br2. Okay? And you can see it's equilibrium, right? The reactions are stable, or the concentrations aren't changing. But now, for the same conditions, look, this is the same temperature and the same pressure. So I've got 10 to the 19 molecules per cubic centimeter of Br2, but I also have 10 to the 19 molecules of an unreactive collisional partner. And so I could even turn that down by an order of magnitude to be more appropriate, like a Dalton's law of partial pressures kind of a situation, right? Where perhaps I've got 0.1 atmospheres of Br2 and roughly 1 atmosphere of my gas bath is what we call it, the second body. And really, this is like having a solvent and a solute, right? Bromine is now my solute, and the bath gas is now my solvent. Look, it doesn't hit equilibrium anymore. Same reaction, but now I'm including an inert body, okay? Because there's nothing that's recycling the bromine back to Br2, which is really cool. And also the low pressure limit, high pressure limit thing really makes a huge difference. I think, oh, look at this. Yeah, my model something wasn't being computed correctly. Yeah, because at 1 molecule per cubic centimeter, there should still be no reaction with this thing. Okay, so good. I think my manipulate model was getting confused. Okay, right, so this makes good sense. At 300 Kelvin, even when I turn the pressure way up, I get no reaction. Good, that's what I expect. But now if I go back to this low pressure limit here, and I start going up in temperature, that's interesting. That's surprising to me. But again, that's why this Mathematica stuff is pretty cool, okay? Because even I can be surprised with observations. So apparently, with 1 molecule, oh, duh, I just realized it. You guys are gonna watch this and like think, man, Harmon was on crack or drank way too much coffee. So why, let's talk about this. Why at 1100 Kelvin and 1 damn molecule per cubic centimeter is there still a reaction? Well, because there's not just 1 molecule per cubic centimeter. I have, where is it? Here we go. I set M, the inert third body, to be 1 atmosphere. Aha. So that's a big difference than how this goes down, right? Where this is 0, now there's truly only 1 molecule per cubic centimeter, okay? But in this reaction now, if I go up to the 1300, yes, there's only 1 molecule per cubic centimeter of bromine, but there's 10 to the 19 molecules per cubic centimeter of something like helium or argon or whatever. So it can still induce a reaction. So that's pretty cool, okay? And so definitely we've already hit that high pressure limit, not because of the bromine, but because of the third body. So to show you the difference in the high pressure limit in this reaction, I would have to start manipulating my third body concentration, okay? Ultimately, the big picture of this, that being said, let me go back to this profile here. Yes, where I start to see now Br kind of start to look like an intermediate. Okay, so now if I want to do some chemistry with bromine radicals. So like, for example, suppose I want to do this reaction, Br2 plus H2. I would get more efficient chemistry out of this by using a non-reactive third body, because now my bromine radical is not getting recycled back to Br2. It's free to now be a part of a more complex mechanism. Okay, so this is often why in gas phase kinetics, if we have a 2-body reaction, so like Br2 plus H2, for example, we often pump in a third body, a third inert body like helium or argon or something like that, okay? If we were to just run this reaction as just bromine plus hydrogen, it's not going to run as efficiently because we're not going to get those bromine radicals, it's not going to run as efficiently because those bromine radicals are just going to turn over to generate more Br2, all right? So all of these are interesting details involving mechanisms. Okay, folks, I'll see you in the next video.